physics has a map of the world. It's called the Standard Model. This map is incredibly successful. It lists the fundamental particles, the tiny building blocks of everything you see, and it describes the forces that govern how they interact. For decades, it has been tested again and again, and it has passed almost every test. It predicted particles before we found them. It explains why the sun shines and how chemistry works. It's one of the greatest achievements of human thought. But it's not the whole story. The map is incomplete. There are parts of the world it doesn't show. There are questions it can't answer. Physicists know this. They see the edges of the map where the details get fuzzy and strange things happen that don't quite fit. They see big blank spaces labeled Herbie dragons. Questions like, what is dark matter? Why is gravity so weak compared to the other forces? Why does the Higgs boson, a particle we found in 2012, have the mass that it does? The Standard Model is silent on these points. So, physicists do what they do best. They imagine. They create new maps. They extend the old one, trying to fill in the blanks. They propose new theories, new ideas about what might lie beyond our current understanding. One of the most beautiful, most compelling, and most frustrating of these ideas is called supersymmetry. To understand supersymmetry, you first need to understand the basic layout of the Standard Model. Think of all the fundamental particles as belonging to two distinct families. They are like two different species that live in the same universe but follow very different rules. The first family is called the fermions. These are the particles of matter, they are the bricks. Electrons are fermions. The quarks that make up protons and neutrons are fermions. These particles are a bit antisocial. They have a property called spin, which you can imagine as a tiny internal spinning motion. For fermions, this spin comes in half units, like 1, 2. Because of this, they obey a strict rule called the Pauli exclusion principle. It means that no two identical fermions can be in the same place at the same time. This is why matter is solid. You can't push your hand through a table because the electrons in your hand and the electrons in the table are all fermions, and they refuse to share the same space. They are the substance of the world. The second family is called the bosons. These are the particles of force. They are the mortar that holds the bricks together. The photon, which carries the electromagnetic force, is a boson. The gluons, which carry the strong nuclear force that binds quarks together, are bosons. Unlike fermions, bosons are very social. Their spin comes in whole units, like 0 or 1. They don't obey the exclusion principle. You can pile as many identical bosons as you want into the same space. A laser beam is just a huge number of photons all marching in step, occupying the same state. They are the messengers, the interactions of the world. So we have this clean division. Fermions are matter. Bosons are forces. Two separate families living side by side, but fundamentally different. For a long time, this was just seen as a basic fact of the universe. Supersymmetry asks a very simple but very profound question. What if this division isn't so fundamental after all? What if there is a hidden connection, a deep symmetry that links these two families? What if you could turn a fermion into a boson, and a boson into a fermion? Symmetry is a powerful concept in physics. It's not just about things looking pretty, you know. In physics, a symmetry means that when you do something, the laws of physics stay the same. If you do an experiment in New York and then do the exact same experiment in Tokyo, you'll get the same result. That's a symmetry of space. The laws of physics don't care where you are. The Standard Model itself is built on deep mathematical symmetries. These symmetries aren't just descriptions, they are prescriptive. They demand the existence of the force carrying bosons. The symmetries tell you how the world must be. Supersymmetry, or SUSY for short, proposes a new radical kind of symmetry. It's a symmetry between matter and forces. It says that if you perform a supersymmetry transformation, you can swap a fermion for a boson. It suggests that these two families are just two sides of the same coin, but if this symmetry is real, it has a huge consequence. It means that no particle can be alone. Every particle in the Standard Model must have a partner, a superpartner from the other family. So for every fermion we know, there must be a corresponding boson that we haven't seen yet. And for every boson we know, there must be a corresponding fermion. The naming is a little whimsical. To get the name of a fermion superpartner, you just add an S to the beginning. So the superpartner of an electron, a fermion, is the selectron, a boson. The superpartner of a quark is a squark. To get the name of a boson superpartner, you add eno to the end. The superpartner of a photon, a boson, is the photino, a fermion. The partner of a gluon is a gluino. The partner of the Higgs boson is the Higgsino. This is a massive claim. It means the number of fundamental particles in the universe is suddenly doubled. For every familiar face in our particle zoo, there is a hidden twin with a different kind of spin. It proposes a whole new shadow world of particles existing just beyond our sight. This sounds like a wild fantasy. Doubling the number of particles just because of a pretty mathematical idea seems extravagant. So why did physicists take it so seriously for so long? Why did thousands of brilliant people dedicate their careers to this idea? Because it wasn't just beautiful, it was useful. Supersymmetry, if it exists, doesn't just tidy up the theory. It solves some of the most stubborn and perplexing problems in modern physics. The first and most important problem it tackles is called the hierarchy problem. It has to do with the Higgs boson. The Higgs is a unique particle, it's a boson, but its job is related to mass, a property we associate with matter. This is through the Higgs field, which permeates all of space. Particles get their mass by interacting with this field. The more they drag against it, the more massive they are. When physicists at the Large Hadron Collider, LHC, finally discovered the Higgs boson in 2012, they measured its mass. It turned out to be relatively light, about 125 giga-electron volts, and this is where the problem starts. According to quantum mechanics, the vacuum of space is not empty. It's a bubbling, frothing sea of virtual particles that pop in and out of existence for fleeting moments. The Higgs boson constantly interacts with these virtual particles. The calculations show that these interactions should add a huge amount of energy, and therefore mass, to the Higgs. The corrections to its mass should be enormous, making it trillions of times heavier than what we actually observe. For the Higgs to be as light as it is, its bar mass, and the gigantic quantum corrections must cancel each other out with an absurd level of precision. It's like having two numbers on a bank statement, one a positive quintillion dollars and the other a negative quintillion dollars, that happen to cancel out to leave you with a balance of just $1. It's not impossible, but it seems incredibly unlikely. It looks like an accident. Physicists call this a fine-tuning problem. It's like trying to balance a pencil on its sharpest point. It's possible, but the setup is extremely unnatural and unstable. This is where supersymmetry rides to the rescue. It solves this problem with stunning elegance. Remember, Susie says every particle has a superpartner. It turns out that the quantum corrections from a normal particle and the corrections from its superpartner have opposite sides. The corrections from a virtual top quark, for example, would be positive, but the corrections from its superpartner, the virtual stop squark, would be negative. So, in a supersymmetric world, every time a virtual particle loop adds a huge chunk of mass to the Higgs, its virtual superpartner loop adds a chunk of the opposite sign, canceling it out. The cancellation is no longer an accident. It's a direct consequence of the symmetry. The pencil is no longer balancing on its tip. It's held firmly in place by guide wires. Supersymmetry protects the Higgs mass and keeps it light and stable, just as we observe. This was the number one reason physicists fell in love with the idea. It felt less like a patch and more like a deep explanation. But the gifts of supersymmetry didn't stop there. It also offered a solution to a completely different puzzle, one that came from the world of astronomy. For decades, astronomers have known there's something wrong with the way galaxies rotate. The stars on the outer edges are moving so fast they should fly off into space. The gravity from all the visible matter of the stars, gas, and dust isn't nearly strong enough to hold them in orbit. The only way to explain this is if there's a huge halo of invisible matter surrounding the galaxy, providing the extra gravitational pull. They call this stuff dark matter. We know it's there. We can see its gravitational effects all over the cosmos. It makes up about 27% of the universe. Normal matter, the stuff we're made of, is only about 5%. But we have no idea what it is. The standard model has no particle that fits the description. A dark matter particle needs to be stable, so it doesn't decay away. It needs to be heavy, and it needs to interact very weakly with normal matter and not at all with light, which is why it's dark. Supersymmetry provides a candidate for free. In many versions of the theory, there is a rule called R parity. This rule basically says that superpartners must be created in pairs, and when they must decay into other superpartners. This has a simple consequence. The lightest superpartner, LSP, has nothing lighter to decay into. Therefore, it must be stable. If this LSP is also electrically neutral, like a combination of Photino, Zeno, and Higgsino, collectively called a neutralino, then it would be a perfect dark matter particle. It would be heavy, stable, and would only interact through the weak force and gravity. It wouldn't interact with light. These particles would have been created in the hot, dense, early universe, and they would still be floating around today, forming the invisible halos around galaxies. It was a astonishing coincidence. An idea invented to solve a problem in particle physics, the hierarchy problem, also happened to provide a perfect solution to a major problem in cosmology, dark matter. This kind of synergy, where one idea solves multiple unrelated problems, is a powerful sign to a physicist that they might be on the right track. And there was a third bonus. The Standard Model describes three fundamental forces, not including gravity: the strong nuclear force, the weak nuclear force, and electromagnetism. These forces have very different strengths at the energies we experience in our daily lives. The strong force is very strong, the electromagnetic force is weaker, and the weak force is weaker still. But their strengths change with energy. If you run the equations and see how their strengths evolve as you go to higher and higher energies, like those present in the first moments after the Big Bang, you see something remarkable. The three forces seem to be heading towards a single point. They almost unify into a single, grand, unified force. But they don't quite meet. The lines cross, but not at the same spot. It's a tantalizing near miss. When you add supersymmetry to the equations, everything changes. The new superparticles also affect how the force strengths evolve. And when you calculate their effect, the three lines, instead of just coming close, meet at a single, perfect point. Supersymmetry seemed to provide the missing piece of the puzzle for the grand unification of forces. So, the case for supersymmetry was incredibly strong. It was mathematically beautiful. It solved the hierarchy problem and stabilized the Higgs mass. It gave us a perfect dark matter candidate. And it allowed the forces of nature to unify. It seemed too good not to be true. The only problem was, we had never seen a single superpartner particle. The argument for why we hadn't seen them was simple. The symmetry must be a broken symmetry. If supersymmetry were perfect, the superpartners would have the exact same mass as their Standard Model counterparts. The selectron would have the same mass as the electron, but we know that's not true, or we would have discovered them long ago. So the symmetry must be broken at the low energies of our world, which means the superpartners must be much heavier than the normal particles. They are too heavy to have been produced in our older, less powerful particle accelerators. This is where the Large Hadron Collider at CERN came in. The LHC is the most powerful particle accelerator ever built. It smashes protons together at enormous energies, recreating for a fraction of a second the conditions of the early universe. One of its primary goals was to discover the particles predicted by supersymmetry. The search strategy was clear. According to Einstein's EMC2, energy can be converted into mass. If you smash protons together with enough energy, you can create new heavy particles that weren't there before. The hope was that the LHC would have enough energy to produce pairs of heavy squarks and gluons. These particles would be unstable and would decay almost instantly, but their decay would follow a specific pattern. They would decay through a cascade of other, lighter particles until they finally reach the lightest superpartner, the LSP. And since the LSP is stable and invisible, it would fly out of the detector without leaving a trace. So, the signal physicists were looking for was not the particles themselves, but their shadow. They would look for events where a spray of familiar particles, like jets of quarks and leptons, shoots off in one direction, but with a large amount of energy and momentum missing. This missing energy would be the telltale sign of the invisible LSPs escaping. The LHC switched on. The data started pouring in. In 2012, there was a huge celebration. They had found the Higgs boson, the final missing piece of the Standard Model. It was a spectacular confirmation of our existing theories. The physics world held its breath. Surely, the superpartners would be next. But then, they looked for specific decay patterns. They looked in every nook and cranny the theory suggested a signal might be hiding. And they found nothing. No selectrons, no squarks, no gluons. The silence from the LHC was deafening. This was a major blow to the idea of supersymmetry. The simplest, most natural versions of the theory, the ones that best solved the hierarchy problem, predicted that the superpartners should be relatively light. They should be within the energy reach of the LHC. The fact that we haven't found them means that if they exist, they must be much heavier than we thought. And this creates a new problem. If the superpartners are extremely heavy, they don't do a very good job of canceling out the Higgs mass corrections. The cancellation becomes less and less perfect as the mass difference between the partners grows. The fine-tuning problem, the very issue SUSY was meant to solve, starts to creep back in. If the squark that partners with the top quark is 10 times heavier, the fine-tuning is back to being around 1%. If it's 100 times heavier, the fine-tuning is extreme again. The pencil is starting to wobble. So, where does that leave us? Is supersymmetry dead? The answer is complicated. Many physicists would say that the simplest, most compelling versions are in deep trouble. The lack of evidence from the LHC has forced the theory into uncomfortable corners. Now, researchers have had to develop more complex, more contrived versions of SUSY to explain why we haven't seen anything. Models like split supersymmetry, where some particles are incredibly heavy and others are lighter, are being explored. But these models lose some of the original elegance. They feel more like patches than fundamental principles. The theory is not technically falsified. It's always possible that the superpartners are just beyond the reach of the LHC, waiting to be discovered by a future, even more powerful collider. But the strong motivation, the idea that it would solve the hierarchy problem naturally, has been significantly weakened. The beautiful idea is no longer a perfect fit for the data we have. Science works this way. It's a tough business. Nature doesn't care how beautiful or elegant a theory is. A theory lives or dies by its ability to make predictions that can be tested by experiment. For decades, supersymmetry was the leading candidate for physics beyond the Standard Model. It was a rich, powerful framework that promised to solve our deepest problems, but it made a prediction that we would find superpartners at the LHCm, and so far, that prediction has not come true. Physicists are now looking more seriously at other ideas. Perhaps the solution to the hierarchy problem lies not in new particles, but in new dimensions of space. Perhaps the Higgs boson isn't a fundamental particle at all, but is made of other, smaller particles, just as a proton is made of quarks. These alternative theories were once on the fringe, but the silence from the SUSY search has brought them more into the mainstream. The story of supersymmetry is a lesson in how science progresses. It's a tale of a brilliant idea that captured the imagination of a generation of physicists. It promised a deeper, more unified view of reality, a world where the distinction between matter and force melts away. It offered elegant solutions to frustrating puzzles, and for a time, it seemed almost certain to be right. But the universe is under no obligation to conform to our aesthetic preferences. The experimental evidence is the ultimate arbiter. The lack of discovery at the LHC doesn't mean the theorists were foolish. Their work was logical, rigorous, and creative. It pushed the boundaries of our understanding and led to new mathematical and experimental techniques. The search for supersymmetry has taught us a huge amount about the Standard Model and what might lie beyond it, even if the final answer turns out to be something else entirely. Supersymmetry might still be out there, hiding at higher energies, or it might be a beautiful dream that just doesn't describe our particular universe. For now, it remains a ghost in the machine, a compelling what-if that haunts the world of particle physics. The search continues, both for superpartners and for other newer ideas. The map is still incomplete. The blank spaces are still there, and the quest to fill them is what physics is all about.